Okay, we're ready to do the second out of the three lectures for this section here, where we're talking about Laurent series and the residue theorem. So the first lecture, we talked about this idea of Laurent series, which is an extension of the concept of Taylor series to functions which are not necessarily analytic. Right? So the premise is that you have a kth order pole, and if you have a kth order pole, what that means is that you have a term which has something like z minus z0 to the k in the denominator. That's sort of what it's saying. So that if you multiply the function through by that quantity, you now have a nice analytic function. And what we discovered last time was that once you have that assumption, you can actually write down your function f of z. It has a kth order pole at the point z0. You can write it in this particular way. So you got your worst possible case is you got some coefficient over here, and you got z minus z0 to the k in the denominator. So in other words, this is z minus z0 to the negative k is what you have over here, and you got a coefficient, and naturally we're going to call that coefficient a of negative k because that corresponds to z minus z0 to the negative k. And then you have smaller powers all the way down to z minus z0 to the 1, right? So if k is equal to 5, you're going to have a 5, then a 4, and so on, all the way up down to 1. And then you're going to have to the power 0. And to the power 0 just means that that's a 0, so you just have a constant. And then you get the normal next powers, right? Power 1, 2, 3, 4, and so on. So you can actually write it in this particular way as a series. So if it was an analytic function, the Taylor series would begin at 0, and you have your coefficients over here. But in this case, because you have a kth order pole, you're going to your index is going to begin at negative k, corresponding to this fact over here. And then and you can now see why you have these indices, because the index is exactly equal to the power over here. So you have an corresponds to the coefficient of z minus z0 to the n. So that's a Laurent series if you have a kth order pole at z0, right? And then we developed a formula for actually finding what these coefficients are, and that's based on just looking at a standard Taylor series of z minus z0 to the k of f of z, and this is just basically based on the Taylor series formula. We got this over here, and remember the lowest value you get is minus k. So here's the way in which we develop the formula. So a to the minus k plus m, and then when you put in m equals 0, you get the lowest value, and so on and so forth, right? So it's given by this thing over here. But I want to write this in a slightly different way. So here you are saying you're taking the mth derivative of this thing over here, and then evaluating it at z0. And by the way, you're allowed to take the mth derivative because this function is now analytic. I mean, that's the whole premise. If you have a kth order pole, that's always going to be analytic. So you can take as many derivatives as you want. So over here, you're evaluating it at z0. So here's a slightly different way of representing that. You take the derivative, and then you take the limit as z goes to z0. It's exactly the same thing because because this derivative has to be continuous. So then the limit is equal to evaluating the function at that point. Okay, so we have this thing here, and you can put in these different values of m. Okay, so that's what we had last time. Okay, now what I want to do is I want to just extend this a little bit and gain some insight into how this Laurent series is going to help us to calculate certain integrals, and we are going to develop the residue theorem by going through this process in a step-by-step way. So in this example, let's suppose f has a kth order pole at z0. Right, so all the previous things in those slides apply, and let C be a small closed loop surrounding Z0 such that F has no other poles within Z0 within C, right? So you have this sort of scenario over here. So there's one pole of our function, and we know that that's a kth order pole, and your C is a curve which you shrink so that there's no other poles, right? It's possible that, for example, that F has another pole out there somewhere, right? It can be a 10th order pole or something, or what have you, right? But you choose your C to be shrunk around your point Z0, your kth order pole Z0. And then here's a rather interesting result. So if you actually take this f of z dz, if you do this contour integral around this closed loop C, which only has this pole Z0, this kth order pole Z0 inside, then what you're going to get is 2 pi times a to the negative 1. And what is a to the negative 1? Well, these are the coefficients of the Laurent series that we are talking about. So this is the coefficient of the power z minus z0 to the negative 1, in other words, of 1 over z minus z0. So this is a fairly interesting result, because even though the Laurent series over here has infinitely many terms, right? So going all the way from minus k all the way up to 0 and all the way up to infinity, there's infinitely many terms. Somehow it just picks out the a negative 1. Nothing else matters. So this factor here turns out to be really, really important, and we'll gain some insight into this as we proceed. So it just picks out the coefficient of 1 over z minus z0, and then there's also a 2 pi which is over here. Does it? Okay. Okay, so that's actually a 2 pi I. So there's a little error there. So that should be 2 pi I times a negative 1. Okay. So why is this true, right? So the point is that what I can do is I can homotope this to a tiny circle, right? And that's what I've done over here. Because there's no other poles, I can just sort of push the curve in, because I can always do that, thinking of this sort of like a rubber band or something like that. As long as I don't cross any other poles, I'm fine. So I can. So when I'm trying to do this integral, I can do it over this green curve instead. And what I've done here is I've just sort of blown up the green curve, just show to just show it, and I'm picking exactly a circular curve which has radius delta, which is centered around the point z0. Now, in the important example, what we talked about a couple of lectures ago, we calculated this for general m, for m being any integer, and we discovered something kind of nice. We discovered that we got 0 in almost all instances, except when m is equal to negative 1. Right, so when m is equal to negative 1, you get 2 pi I. How did you discover this? Well, we just parameterize this, right? So your z minus z0 is this vector here. You can just think of that as delta e to the I theta, and theta goes from 0 to 2 pi as you traverse the circle, and then you just work through the parameterization, and you get this. Okay, so that's something that we figured out. So this means then that so let me correct this. So that should be an I times a negative 1. So this means then, okay, so let's see how this can be used, right? All right, so when I take this integral, so what I'm going to do is I'm going to take this integral over C. Now C is this homotoped curve that I have over here, but I have f of z represented as a Laurent series in this in this particular way. So I start at negative k, right? So if k is 3, for example, I start at negative 3, then I have a negative 2, negative 1, 0, 1, 2, 3, 4, and so on and so forth. So this is my representation of my function f. Right, and then what do I know? Because when I do this, I just have these constants, coefficients multiplied by this, but all of these n's correspond to integers, and by this expression that we have over here, I'm going to get 0 in every single instance except when I have a negative 1 over here, right? So when I have a negative 1, that's when n is equal to negative 1, and that's a negative 1. So this is the one case when I don't get a 0, right? So all the others are going to be 0. So I have this here, and then what I can do is I can factor out the a to the negative 1, and then I apply the fact that this is going to equal 2 pi I, and then I'm done, right? So a negative 1 times 2 pi I, that's what I claimed that this was. Okay, so that's pretty neat, that when you're doing your function with that kth order pole, you have a small enough contour around that pole, and then when this integral, it's just going to be equal to that. So if you know what a negative 1 is, if you have a nice expression for a negative 1, you can just do this immediately, and that's what we're going to try to do. Okay, so let's keep that in our back pocket, and let's define something called the residue. R-E-S-I-D-U-E. So the residue of a function at a point z0 is going to be this thing over here. So the residue, so here's our definition or notation. So residue of a function, so you put in a function at a certain point, right? So this is sort of like calculating the function at that point. It's not f at that point, but it's something else related to that point, and we call that the residue. What we do? Well, what we do is we do an integral of this form where you take C to be a closed contour around z0 such that there are no other poles inside. right? So you take a small enough pole, you do this calculation, and then you divide by 2 pi I, and that's called the residue of the function at that point. Let's see whether we can establish a connection with what we've just done, right? Well, what we just did was that if I want to calculate this, what we just figured out is that if this had a kth order pole, what you get is 2 pi I in a negative 1. Right, so that's what this is going to be, 2 pi I a negative 1. So then the residue of f at z0 is going to be, well, you have this 1 over 2 pi I over here, and then you got 2 pi I negative 1, the 2 pi I is cancelled, and you get a negative 1. So the residue is essentially the Laurent series coefficient of the term which has power negative 1. That's it. Right? So the residue is equal to that. So here's the way in which you define the residue, but based on what we have established in the previous example, this is just going to be the coefficient a negative 1. So how does that help us? Right? Okay. Now we have a formula for finding the Laurent series coefficients, and it's given in this particular way. Right, so a negative 1 is clearly something which is of interest to me. So how can I figure out what a negative 1 is? I want this to be negative 1. So what I want to do is I can put in m equals k minus 1, because then I've got a k minus 1 over here. The k is cancelled, and I'm ending up with negative 1. Okay, so I put in m equals k negative 1, k minus 1 in this. So I have 1 over k minus 1 factorial, and then I have the mth derivative, so I have to have the k minus first derivative, and then this is just z minus z0 to the k f of z. So here's a very nice formula for a negative 1 if your function f has a kth order pole, and this is easy to remember. If it has a kth order pole, by multiplying by z minus z0 to the k, you're actually getting an analytic function, which is why you're then entitled to take derivatives and so on and so forth, right? But you have to take k minus 1 derivatives, and you've got a k minus 1 factorial over here. So here's a formula. Okay, so now what we can do is just put everything together. We figured out that this was equal to a negative 1 if you had a kth order pole, but in the previous slide we figured out that a negative 1 was equal to this, right? So this is an important formula. So we're going to call this the residue formula. It tells you the residue of a function f at a point z0, which is a kth order pole. If it's a kth order pole, you have to do this particular calculation in order to figure out what that residue is. Okay, so we've done some connections here between Laurent series and a negative 1, which is the coefficient of the power 1 over z minus z0. And then we've defined this residue, and in terms of the residue, we've got this here. Okay, so let's just do an example before we get to the main result, which is the residue theorem, which is going to link this to integrals in a very, very nice way. Okay, so let's just understand, try to make sure that we understand how to calculate the residue, right? So let's look at this function here. It's sine z over z minus 2 squared times z minus I. So that's a function, and you're asked to find the residues at these 2 points, z0 equals 2 and z0 equals I. Well, why is that? Well, these are the poles. You can see that those are the poles that are available. Okay, so let's look at z0 equals 2. So you can see that that's a second order pole, because you have to multiply by z minus 2 quantities squared to eliminate this, to get rid of this. So that's a second order pole. So then if I calculate the residue of f at the point 2, so here's my residue formula for a general kth order pole. If I have a second order pole, I have to put in k equals 2. So if I put in k equals 2, 2 minus 1 is 1. So that's 1 over 1 factorial. And if I put 2 there, then I just get the first derivative. So here's what I need to figure out. I need to do that calculation. So if I look at what's going on here, I have z minus 2 squared times f of z. So essentially, I'm trying to get rid of this. Yeah, I try to get rid of that and then make that an analytic function. So if I cross that out, I'm left with sine z over z minus I. Right, so this is now differentiable in a region which is very close to the point 2. Right, so this only has a problem at z equals I. Okay, so how can I do that? Well, I mean, this is just your standard derivative. I have to use the quotient rule. So z minus I times cosine z minus sine z times 1 over z minus I quantity squared, and then I have to take a limit z going to 2, which amounts to just sticking in z equals 2 directly into that expression. And if I do that, I get this expression over here, right? Just putting in z equals 2, and it's some complex number, right? So I'm not really going to try to simplify this. It's this complex number that I get when I when I do this calculation, right? So this number, if you really want to, you can write this in the form a plus ib, but I'm not going to waste my time on doing that. So here's our residue at the point z equals 2, right? Residue f at the point z equals 2. Okay, let's now do the other thing at z0 equals I. So here's my residue formula again, but when this just has a power 1, so it's a first order pole, right? So it's a first order pole. So in order to get a first order pole, what I have to do is I have to put in k equals 1 into my expression over here. So k equals 1. So if I put in k equals 1, I get 1 minus 1. So 0 factorial is by definition 1, by the way. And then I put in k equals 1 here, right? So when I put in k equals 1, I get to the power 0. So differentiate 0 times, essentially, is what that's saying. So then you can just simply forget about that. Right, so you simply forget about that, and over here I have z minus z0 to the 1, because I put in k equals 1 times f of z. So what that amounts to is, again, so I'm just multiplying through by that, so I'm left with this term over here. So I'm left with that term over here. I do not need to take a derivative because this is the 0th derivative, so I just have to do this calculation, and that's easy. Again, what I do is I just stick in z equals I, and then I get this, right? So that's what it is, right? So that's my residue at that point. So now we have an understanding of how to calculate the residue of certain functions when you have different order poles. Okay, now we're in the position to write down the major theorem, right? So this is essentially the major theorem in complex calculus that we're going to deal with in this course, and it's called the residue theorem. Okay, and it's going to tie together what we've discussed so far. So let f be analytic in a region A, except at a finite number of points z1, z2, all the way up to zn, which are inside a simple closed curve C. Right, so it's analytic in some region surrounding this, except at these problem points. So the problem points are inside a curve C. Right, so you have z1, z2, z3, you can have a z4 and so on. So there's n of them, right? So there's n of these problem points. Okay, so this tells you, for example, that the function is not analytic inside, right? Because it's got these problem points. If it were analytic inside, then Cauchy's integral theorem would apply, and when you're taking the contour integral around the closed loop C, you'll just get 0. But it's not analytic, you have problem points, right? And then it turns out that when you're trying to calculate this, the answer should be 2 pi I times the sum of the residues. This is just telling you adding all the residues at each of these points, each of the problem points, right? So there's n of them. So you calculate the residues at each of those. You just add them together and you multiply that by 2 pi I. That gives you the value of this contour integral. So evaluating contour integrals just amounts to trying to figure out what these residues are, but these points have to be inside the curve, right? So if I have a point outside here, it's not relevant. It's just the points which are inside. They're inside the simple closed curve C. Okay, why is this true? Well, what I can do is I can homotope to tiny curves around each of the ZJs. So here's an example when I've got 3 different problem points, Z1, Z2, and Z3. So there's no other problem points. So I can push my curve C, my yellow curve, until it's essentially the green curve. So this is sort of like this dumbbell type structure, but then you go to all of those curves, right? So the integral is going to be the same as the integral over the green curve. But then I do this argument that, these are these bidirectional I'm going that way along that and coming back along that, and I'm thinking of shrinking these so that they're one on top of the other. So then I'm going to get negative. If I do this calculation, I'm going to get negative of what I get in that calculation. So those cancel out. So then I'm left with essentially 3 small loops. So I need to do the integral around the small loops, right? Okay, so the integral around the closed curve C, the yellow curve, is going to be the sum of the integrals around these tiny little loops around each of the poles, around each of the singularities. So that's all that this is saying here, right? So I just have to add together the green curves, the summation over each of the green curves. But the green curves are such that you shrunk them so that there are no other poles there. And because there's no other poles there, by definition, this thing is 2 pi I times the residue at that point, because we define the residue as 1 over 2 pi I times an integral of this form. Okay, so this integral I can write as 2 pi I times the residue at that point. And then we're essentially done, because all I do is I just pull out the 2 pi I, and that gives me my formula. Okay, and that's it. right? So that's our proof of the residue theorem. So what we're going to do next time is we're going to go back and look at this residue theorem, which is this really nice result over here, and we are going to see that this is incredibly powerful, and it can help us evaluate all sorts of integrals, and we can also establish connections between with things that we already know, like the Cauchy's integral theorem and Cauchy's integral formula. So that's our second lecture.